Okay everyone, today we're going to talk about special triangles, and to do it, the first thing I'm going to do is I'm going to draw a square. And one of the things that I know about squares is that all the sides are the same length, so I'll call them x. I also know that squares have right angles. The next thing I'm going to do is I'm going to draw a diagonal here, going straight across. And I'm going to let the length of this diagonal be 1. And one thing I notice is that when I make this diagonal, I cut this angle in half, so this is 45 degrees, and this is 45 degrees. And so I'm going to spend some time to find out what x is now in this 45, 45, 90 triangle. And so to do it, I can use Pythagorean theorem. I know that x squared plus x squared has to be 1 squared. Well, that's 2x squared is equal to, well, 1 squared is 1. So x squared is equal to 1/2 when I divide by 2. If I take the square root of both sides, I get x is equal to the square root of 1 over the square root of 2, which is 1 over the square root of 2. Now, I'm not allowed to leave a square root in the bottom. It's bad grammar in mathematics, so I multiply by 1. Because when I multiply by 1, it makes it look different, but it's the same, even though this is a funny looking 1. And so when I multiply by 1 there, I get square root 2. Root 2 times root 2 is 2. And so these sides here are not x, but rather root 2 over 2, and root 2 over 2. And this is one of our special triangles. It's an isosceles right triangle. Well, this is 45 and 45 degrees. The hypotenuse is 1, and these two sides are root 2 over root 2. And that's a 44 for my drawings, I guess. A 45, 45, 90 triangle. That's a handy triangle to know. There's one more triangle. Let's take a look at this triangle here. We're going to draw an equilateral triangle. We'll do it here. And that is about equilateral. And when I draw my equilateral triangle, I'm going to have every side be of a length 1. And I know that this is 60 degrees, 60 degrees, and 60 degrees. And then what I'm going to do is I'm going to come along and I'm going to draw on here an altitude. Okay? And when I draw that on there, I create a right triangle where this angle here is 30. This length is still 1, but this length now, the altitude cuts it in half. And so I'm only looking at this green triangle here. And if I want to find what this altitude is here, which I can call, let's call it x for now, I know that x squared plus 1/2 squared is equal to 1 squared. Well, x squared plus 1 squared over 2 squared equals 1. X squared is equal to 1 minus 1/4. Well, I know that is 3/4. If I take the square root of both sides, I get the square root of 3 over the square root of 4, which is square root of 3 over 2. And that's the measurement of the height of this triangle, square root 3 over 2. And so this is another special triangle called a 30, 60, 90 triangle. Very creative names mathematicians have come up with. And so a right angle, this is 60, this is 1. The smaller side is half of the hypotenuse, and the longer leg, this is a short leg, is root 3 over 2. And that's another special triangle. And those ones we need to be aware of. Let's try some examples that use these special triangles now. So, using your two special triangles to determine the following, no GDC allowed. I want to find the cosine of 60 degrees. Well, if I take a look at my special triangles, here is that triangle. Special triangle, it's right. Here is 60 degrees. Cosine is adjacent. The cosine is the adjacent, which is this side, over the hypotenuse. So that's going to be 1/2 divided by 1, which is simply 1/2. Excuse me. Well, that's awfully convenient. So this side here, the adjacent side, is cosine. If I look at tangent of 45, I'm going to grab my 45-degree triangle. If I choose one of the angles to be 45, tangent, we remember, is opposite over adjacent, is tangent. Well, the opposite of 45 is equal to root 2 over 2. The adjacent is also equal to root 2 over 2. Well, together that equals 1. So tangent 45 is 1. If I do the sine of 45, well, the sine of 45 is equal to the opposite over the hypotenuse. The opposite is root 2 over 2. Hypotenuse is 1, which is simply root 2 over 2 is sine 45. This one's root 2 over 2. And finally, cosine of 30 degrees. I go back to my 30, 60, 90 triangle. Cosine I know is adjacent over hypotenuse. Well, from 30, adjacent is equal to root 3 over 2. Hypotenuse is 1, so over 1 is just root 3 over 2. And so these special triangles, I can find the exact value of sines and cosines of 45s, 60s, and 30s. So now let's note, you see, given this triangle here, I want to solve for x. Well, if I know this is 30, this here is opposite of 30, and this is the hypotenuse. So that's the sine of 30 degrees is equal to the opposite over the hypotenuse, which is 10. Well, solving for x is equal to multiply by 10 sine of 30, but I can't use a GDC. But what I can do is I can use my special triangle. And when I use my special triangle, I know that sine is opposite over hypotenuse. So the sine of 30 is equal to the opposite over the hypotenuse, which is 1/2 over 1, which is 10 times 1/2, which is 5. And so x here is 5. One more example. Now we have 10 root 2 and 10. And if I look here, here's my 45, 45, 90 triangle. And if I think about similar triangles, if I would shrink this down or make it bigger, the sides are changing. And they actually have different lengths. And if I would take this triangle of 1 and root 2, if I would multiply 1 times 10 root 2, if I would take 1 and multiply it by 10 root 2, I would have to take all these sides also multiplying by 10 root 2. And when I multiply root 2 over 2 times 10 root 2, I end up with 10 times 2 over 2, which is equal to 10. And so these values here fit the proportion of the 45, 45, 90 triangle. And so these values of x are 45 degrees. And this will also be 10. And I know that even though in this case it's the legs that are root 2 over 2, here the hypotenuse has a root 2. When I do the math, convert it by making a larger triangle multiplying by 10 root 2, I end up with 10 and 10, and so they are similar. And so these angles here are 45. So the key to this problem, or to special triangles, is just knowing these and using sines and cosines and tangents to find values for them. And they come from an equilateral triangle and a square.